Your next unit, and by the way, this has all pretty much been unit one, and I don't think it's quite officially done. We'll come back and tie up some loose ends, but this last unit has been all equations and inequalities. Your next unit is going to be over what we call functions, and get used to that word, functions. You're going to hear it like, I don't know, 7,912 times.
I
So
know the teacher is going to play the song for us.
the
Conjunction
I
action.
could play conjunction junction. What's your function if you'd like?
Down in a like, please no.
So there are all sorts of different questions that will arise pertaining to functions. This is not, it's always an awkward sort of thing in algebra. What I try to do in algebra is introduce you to what it means to be a function. And then I try to introduce you to some things like, how do I evaluate a function? How can I look at a graph and tell if it's a function? How can I look at a set of points and determine if they define a function? There's all sorts of perspectives on this, but today will be a little bit of a clumsy one just because I'm trying to get a lot of basic concepts out. So the first thing you have to know is the definition. And a function is a relation.
Do we need to write that?
Uh-huh. That definition should make almost no sense, by the way. And so I don't want you to sit there as you write it down and think, gosh, what's wrong with me? Nope, it's not you. It'll make more sense as the hour goes on here today. So I'm going to show you, and once you're done copying this definition down, I'm going to show you on the computer an example of a function. And then I'm going to show you an example of something that's not a function. In fact, I don't even think I need to use the computer. I'll just make one up. And you can do this in your notes too. So that this will actually be better if I don't use the computer because then you can kind of mimic what I'm doing. So on your notes, you can just draw a little x-axis and y-axis like this. So something like this is a function. And the thing that's going to start flooding into your brain, your understanding, is that inputs are, this is a real sloppy way to say this, but I talk sloppy a lot because I think sloppy talk makes more sense than big fancy college professor talk. Inputs are generally your sideways, like your x-axis numbers, and outputs are generally your y-axis, your uppy downy numbers. Even when the variables change and we don't use x and y, the independent variable, the input one is the one that's on the sideways axis, and the output is on the vertical axis. So for the reason I know this is a function is because I could go anywhere on the x-axis and make a point like right here. And you would ask yourself at this point, how many purple points are associated with that yellow dot? How many are there?
One.
One, and exactly one. And if I zoom in on this a little bit for you, you can see that when I go to that location on the x-axis, there is 1 point below me, and it's right there. And I could say the same thing about every other point on this graph. I could go anywhere I want on the x-axis. For example, I could go to right over here with this other yellow dot. And eventually, if I travel downwards, you would agree that someplace down here, ping, there is a single point. Don't worry about it. There is a single point associated with that xness. So, like, let's just say hypothetically that this number over here was like when x equals 3. You can see that for an input of 3, there is exactly one output of like -1 or -2. Or let's say that this input over here, I'll just make this up, is like -7. You can see again that there is only going to be 1 point that is associated with that horizontalness. To be a function, you should be able to look at a graph and say that for every horizontal place I would ever go to, there's never more than 1 point above or below it. That's a very lazy sort of casual definition of what it means to be a function. Can you guys think of what it would look like and this is maybe too early for this question, but let's in our notes make a sketch over here of something that's not a function. So we'll draw another x-axis, y-axis. Can you think of what we could do with our pencils to make a graph that does not meet the criterion? And again, maybe way too soon for a question like that. Go ahead, say it.
And curves like from one side all the way down to like the same side, just a different function.
Maybe like this, maybe?
Yeah.
This is not a function. Good. And the reason why it's not a function is because now if I pick a point on this graph, so if I went on the x-axis, say to right here, there's not uniqueness anymore. The thing about that other graph that we just had was you could never say, which purple point do you want me to pick? You could, but then people would probably ask that you be institutionalized or something. Like there's never a dilemma with this graph as to where you want me to go. Like if you give me this X right here, then I know to pick this Y. You give me this X, I pick this Y. You give me this X, I pick this Y. Like there's never a decision. That's the essence of being what we call a function. If you're not a function in mathematics, there's going to be options. And you can see that if I travel out to here on the X-axis and say, pick me the Y that goes with it, you guys are all pretty bright. Do you see how you have a choice?
Yeah.
That choice renders this not a function. This is now just what we call a relation. All graphs are relations, for the record, but to be a function, you have to be a little bit more special than that, in that you have to not ever have a choice of, do I go to this Y value or this Y value? Mm-hmm.
So, doesn't this correlate with like the nonlinear?
It will, yes. And I mean, the concept of linear is more specific than this. Like we will talk specifically about linear functions a lot. But the goal for today isn't so much to worry about linear versus nonlinear, but rather today to worry about just what is a function, right? These are both obviously nonlinear, correct? So in the case you're lost right now, if you traveled out to this x-axis point, you would agree that you could select this green point or you could select this red point. And no one could disagree that those are both points on the graph that are associated with the yellow dot, right? Mm-hmm. You can. I'm just saying that the fact that you're able to means it's not a function. To be a function in mathematics means that if you put in an input, it will always give you one output. And this is not a proper function because if let's just say hypothetically, I pick a number for this. Let's say it's 2 on the x-axis. If I put in 2, I need my machine to be reliable. I need it to always return the same answer. And if it, returns this answer for Cooper, and then it returns this answer for Seth, that's not a function. Functions are reliable, repetitive, predictable, and a single input should never return more than one output. Okay? So, and the whole thing about us picking is kind of like we're not really picking. I'm just saying if you have the option to pick more than one, it's not a function. If you've learned anything about this before, you know that to determine if something is a function, you use something called the vertical line test. And you're going to hear me say this again hundreds of times. The vertical line test is, you guys have all probably helped your mom or dad. Like if you've ever tried to hang like a really heavy mirror on a wall, you know that you don't probably want to do that with an anchor and sheetrock. You probably want to get some things into some studs, right? So your moms and dads in their toolboxes, every one of them, I'm sure, has a stud finder. And I would equate this kind of like with a stud finder. Like, you know how you push the button and you scan it across? That's kind of how I view the vertical line test, is the vertical line comes across. And all you have to ask yourself is this: would my vertical line ever see more than one point on the purple graph? And the answer is yes, it would. We can all agree that like right here, it goes off and it pings, but it's pinging the purple graph twice. It pings it once and it pings it here. That's called the vertical line test. There's no one in the world of math that would not know what you meant if you talked about the vertical line test. But on the other hand, let's look at this other graph just so you can see when something passes the vertical line test, what it feels like. Look at this vertical line and imagine it scanning through this purple roller coaster. Does it ever see the purple graph more than once?
No.
Never. It pings it once and it passes right through. So that's the essence of being a function, is that you have exactly one y for every x, no more. Got it? Okay, so that's to me the clumsiest, maybe, and most awkward part of this lecture is just to get that out there. That's the definition of a function, a relation in which each input has exactly one output. There's kind of the big picture. Now I'm going to start cruising through some delta math sections with you so you can see what you're up against, because there's a lot of sections in this assignment. So the first one is identifying functions from a graph. So here we go. So you're going to be given some problems like this, and I'll zoom in a little bit for you here so you can see. Does this little tiny graph represent a function?
No.
Yes, it does. And the reason it does is because it passes the vertical line test. If you scanned a vertical line across this graph, and I can zoom in even more so you can see, we all agree that the vertical line is never going to quote unquote see this graph more than once? So we would answer on this one that yes, it is a function. All right, so to be a function, you simply have to pass the vertical line test. Can I get a new problem? I wonder, do I have to? Oh, it's animating. It's showing you the vertical line. I forgot that it does that, which is actually kind of neat. Is this a function? Good. You guys got the idea, right? You can clearly see that the vertical line test is going to double ping, right? So this one we would pick not a function. And so you're going to be given some graphs in the assignment. I don't know how long how long does it make me sit there and watch that? I just have to scan down to it. Function? No. Function? No. Function? Function? Yes. Right. And so you can see that even when graphs start to look like they're climbing vertical, a polynomial function like this never achieves pure vertical. So this would be a function. There's also going to be a level 2. I don't exactly know what that means, but let's take a look at some of these. Is this a function? Yes, it is. Good. Is this a function? It is not. If you said yes, I have failed you in this lesson. You can clearly see that a vertical line, when pinging through, and I don't have a good vertical line tool here, but if I graphed a vertical line like right here, do you see how it would ping the graph twice? So clearly not a function, right? Any graph that exists at any point above or below itself is not a function, bottom line. Do you have any questions about that concept? Okay, so let's go back now and talk about how can I tell if something is a function if it's just a set of points like this. Like this. So here's another batch of questions that you're going to be asked to do. This one does not have a graph. Sorry, guys.
Couldn't you just get a graph and graph it?
You could. How do I take the knowledge of what we just saw with a graph and apply it to a set of ordered pairs like this? Like think about 2 points that are above and below each other. What's true? Like I'm holding up my hands right now with 2 points above each other. What's true about my 2 points? What makes 2 points be vertically in line with each other?
Okay.
The X and Y.
Something about the X and Y, I agree. And I heard someone say the same Y-axis, and that's not true. But so let's imagine that you graph a point. So here, let me just make a really half-hearted sketch. So here's my X-axis and Y-axis. If I put a point right here and a point right here, what do they have in common? They have the same X coordinate, don't they? So if I know that even if I don't have a graph, even if I don't apply the vertical line test, someone asked, well, I could just graph them. Well, of course, but nobody got time for that. Like, I don't want to be sitting around graphing all the points. I'm going to look for points that have the same X coordinate, but different Y coordinates, because that will tell me by definition that they are above and below each other, right? So do you see, it says, the question on this one says, which is not a function. Can you find me one that clearly is not going to work?
The last.
The last one is a function, isn't it?
The last one is a function, and I can prove it to you because look at the x coordinates on the last one. -1 goes up to 2. 9 goes down to -9. Have I circled any red numbers that are the same?
Yes.
I have not. There is a -1,
No.
a 9, a -9, and a 0. Those are all unique. Which one is it, Gunnar? The second one is not a function. And you can see that it's not a function because this point is left 6 up 5. This point is left 6 up 3. Both of those points are going to be left 6. One goes up higher. Clearly, they are in line. The fact that there's a -6 in this point doesn't actually matter because it's a y coordinate. What we're looking for is 2 points with the same horizontality and different verticality. So on this one, since it says which is not a function, I would obviously pick B. So let's try another one of those. Which does not represent a function? Again, the second one, and you just zoomed right in on it, didn't you? And what makes it fail the vertical line test is the fact that this point is right 4 up 7. This point is right 4 down 9. By definition, they are above each other. Got it? This time, the question is, which of these does represent a function? Does A pass the test? No, because of the 2 6s right away. Same X's, different Y's, you're out. Does B pass the test? It does. So I pick B. If it's not going to give me like choose all that apply, then I already know that C and D are going to fail because B passed, right? All of B's X's are unique. He's got a left 8, he's got a right 4, a left 5, and a right 8. Those are all unique, so we would pick B. So that's another section of problems. Do you have any questions about that? Okay. The next topic is going to be the same thing. However, it comes at you from a different perspective. This is what is called a mapping diagram. These will be the ones that will be hardest for you to answer in Delta Math. So, ready? First off, have you ever seen one of these before? It's okay. How many ordered pairs do you think this mapping diagram represents? Who said 4? Who said that? 4 is correct. One of the ordered pairs, I can tell you right now from this mapping diagram, is -2, 9. You can see a mapping, an arrow that goes from an input, an x of -2, and it maps or outputs to 9. Do you see it? That's an ordered pair. Give me another ordered pair from this mapping diagram. Go ahead.
-4, 7.
-4, 7. Give me another one.
Negative.
-4 also maps to -1. And then give me another one.
0 to negative.
0 maps to -1. And you can clearly see when I write it like this, why this is not a function, correct? Because the input of -4 is mapping to 2 different outputs.
That whole thing you had to start in the first place just made a whole bunch of
What I have to ask myself is, do I really want to sit here and write out these points every time? And the answer is no. So what I want is like, for a graph, I've got this visual awesomeness called the vertical line test. For my points, I just look for repetitive X's. What is my visual cue with a mapping diagram for me to look at it and say, you, sir, are not a function? What is it, Gunnar? Yes. We call this divergence. When 2 arrows are leaving from the same location, they're like 2 ships leaving from the same port. Their paths diverge. You've heard that word in English before. You go north, your friend goes east, you guys diverge, correct? So when 2 arrows are diverging from the same input, that's my visual cue right away to say this is not a function. -4 is spawning 2 outputs. So on this one, do you understand so far?
Yes.
Because now's the hard part. Are you ready? Look at all these answers. And I don't want you to feel like you can't do this. So here it goes. Every year I give these, and because I love the problems, there's just a little bit of a learning curve. So here it goes. First of all, does the mapping diagram show a function? No, we decided, so we're going to pick does not represent a function. Now you need to understand what you're saying, or these questions will never make sense. So here it goes. The mapping diagram above does not represent a function since there is one number in the input set A where there are multiple mappings to set B, the output. Do you see that? Don't worry, we're gonna do this again. Let's go again. New problem. Is this a function? Yes. By the way, what do you think the word is that we would use for these two arrows coming to the same place? There's a word in English for that. Say it again. Converge. Very good. So divergences, you're not a function. Convergences, it's fine. Two different inputs can go to the same output. So now we get to try to answer the question. Are you ready? Here we go. What are we going to pick for this first one?
Shows a function.
The mapping diagram above represents a function since for each number in set A, there is only one mapping to set B, the output. Do you see it? You will not struggle with this section if you understand the words you're saying. If you understand what it means to map and inputs and outputs, you can reason your way through these. Let's go again. Is this a function? Yes, it is. You look on the left side, the input is like, no, none of my inputs are diverging, so I'm good to go, right? So here we go. Help me with this. The mapping diagram above represents a function since for each number in set A, the input, to make sure you pick the input. Why they put input and output, this is like, that's sadistic. Make sure you pick input and then output. There is only one mapping to set B, of course, the output set. Every year, these questions cause headaches. Is this a function?
Yeah.
Yes. Okay, let's pick another one that is not a function. I'll just keep going until I find a bad guy. That's a function. That's a function. Okay, now it's just toying with me. Hey! Function?
No.
No. Who's the bad guy?
6.
6. 6 is like, watch me. I'm a joker. I'm going to go to -3 and then I'm going to go to 0. I can't do that. So here we go. The mapping diagram above does not represent a function since there's one bad guy in set A where there are multiple mappings. You guys are amazing to set B. Okay. So don't be intimidated by all those check boxes, but it's really testing your ability to understand the language of function, not a function, input, output. So at this point in the lesson, you know what a function is. You know how to look at a set of points and determine if it's a function. You know how to look at a graph and determine if it's a function. And you know how to look at a mapping diagram and determine if it's a function. Now comes the easy part of the lesson. And if that was easy, this is going to get easier. Unless you hate math, then this will be your least favorite part. The last thing we have to do is evaluate functions. And again, I'm just giving you notes this way because I thought it would be easier. So there's a function up there on the board. His name is f of x. And here's what f of x does. He's like, I have a job. As programmed by the math gods, my job is to take whatever x you give me and multiply it by 2. And then whatever answer I get, I'm going to subtract 2. What do you think? You're all so good. What a lucky, I'm lucky. I got good kids this year. What do you think we're going to do with this -3? We're going to plug it in. Yep. We're going to just take -3 and we're going to plug it in right there. And we're going to do some little kitty math. Are you ready? So if I want to do f of -3, I'm going to do 2 times where x used to be minus 2. Put -3 in there. What's 2 times -3? What's -6 minus 2? I'm just going to go down here to the box and I'm going to type in -8. And that means that my input of -2 or -3 yielded an output of -8. And then I click submit and I get my little green check mark and I go again, rinse and repeat. How about this one? What does my function do? Describe it to me in English. What does this function do? When I feed it a number right where that arrow is pointing, what does my function do to it first?
Wait, so never mind.
That's a negative.
It puts a negative on it. What if it's already got a negative? Then it would take the negative off. That's what negatives do. And then what does it do after it's done screwing around with my number?
Go bye-bye.
What does it do at the end of the function? I'll point to it for you. It subtracts 1. Functions are little machines. So if I put 0 right there, what is the negative or opposite of 0? And what is 0 minus 1?
-1.
So I just go down here to the happy little box and I type in -1. And you know, on Delta Math, if you hit enter twice, you can submit.
Yep.
Save time. Sure, fire away.
So now at the very end, then we add in after we like plug in our number. Could you do it in the very beginning or would that change?
We just do it right now. Like, you ready? See the purple box? That's the function rule. All I'm going to do is go into that box, and every time I see an X, I'm going to put this number right here. Boom. Does that make sense? The answer is +6 for this one. Do we all agree? Because what it's going to do is it's going to take the negative of -4, which is 4, and 4 plus 2 is 6. Do you have any questions on this one? There's one more section to go.
So we're basically just plugging the number.
You're plugging numbers into a function, and then it'll go beep, boop, 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 and it vomits out an answer, and you type the answer in the box. Got it?
Seems pretty understandable.
The last one is evaluating quadratic functions.
Quadratics.
Are you ready?
No.
This is it, home stretch. I know it's a lot to ask a room full of teenagers to sit and listen to this for this long. We're 4.5 minutes away, so let's finish strong, okay? This is it, last section.
Yes, sir. Aren't quadratics really a pain in the butt?
Not in this context, they won't be. Quadratics are going to become more difficult when we have to factor them and graph them and stuff like that. All I'm asking of you today is to understand this. Inside this red box is what we call a function rule. This is the meat and potatoes. This is where the rubber meets the road.
Well,
This is where the math is happening, is inside of this box. I'm sorry to ask questions like this because they're almost insulting, but how many X's do you see inside the box? 2, right? I see 2. I see 1 right there, and I see 1 right there.
We're only supposed to have one.
What am I going to put in place of those X's?
A -8.
A -8. So here's what we're going to do is we're going to show our work. Those last problems, I don't think I needed to show my work. That was pretty easy. These ones, I'm going to show my work. And what it's going to look like is this: -3 blank squared minus blank minus 15. I just basically rewrote the red box, but every time I saw an X, I just put it in an awkward void. That awkward void's going to sit there and say, feed me a number, feed me a number. And what am I going to put in those awkward voids?
-8.
-8. Not any number, but the number that was designated as my input, right? Now, you better know the order of operations. Inside my purple and red math problem, what has to go first? There are no parentheses, by the way. These are just multiplication closure signs. Exponents always go first. And so I'll draw a little green box around this for you. And make sure you have a calculator with you. What is -8 squared? 64. So this is now going to be -3 times 64. What's going to happen right here inside this little red rectangle?
Is it going to become a +8?
It's going to change to plus. The negatives and the minuses, they kind of become a plus. So then we have +8. Guys, stay with me, okay? There's a lot of squirreliness happening, and I'm not done. Okay, I need you for another minute. You're not helping my cause at all. Good still? Exponents go first because there were no parentheses. Again, those parentheses, we only call them parentheses when there's math to do inside. These are just closure things. Don't worry about those. Exponents done. What goes next? Multiplication. Can anyone do -3 times 64? Would you believe me if I told you it was -192? Okay, you should believe me. That's what it is. And then we're going to add 8, and then we're going to subtract 15. If you owe me $192 and pay me back 8, how much do you still owe me? That's right. -184. And now if you owe me 184 and borrow 15 more, how much do you owe me? -199. So you just go in the little box, type in the answer, and that is how you
Hey, wait, don't do that yet, please. I want to write this down.
got it. So we covered a lot of ground today. You guys did really well until those last couple minutes. Most of you did well the whole time. Thank you. Tomorrow and Thursday, you're going to have some jumbo assignments. You will work hard in class. I hope that for your sake.
See you Monday, right?
Yeah. Monday, I'll see you back here. Right.
So, how much hours will we be here?
What is that? 5 days? What's today? Tuesday? 6 days. 143 hours and 15 minutes.
Thank you, Mr.
Jeez. How do you know that?
Because it's 6 days, and 6 times 24 is 120 plus 24, which is 144. But then we have to subtract the 45 minutes for the class we just had. So it's 143 hours and 15 minutes.
Not for your own good, Mr. Aaron.